Welcome everyone to this third presentation in the series, Forging Ahead. You see, the title is Analysis and Synthesis, Restoring the Ancient Technique of Mathematical Discovery. This is one of the most liberating things a student or professor of mathematics can know. It is a tragedy, in my opinion, that this technique got lost along the way in mathematics, but I'm here to restore it. Let's get to work. Analysis and synthesis is hard to pronounce. Analysis and synthesis provides a new space for thinking. Knowing about this method can be truly liberating for any mathematician. It is as if two symmetrical modes of doing mathematics are opened to one's view. Analysis is one world, and synthesis the other. The original meaning of the word analysis has so fallen from use that many mathematicians do not know what it even is. It is working backwards from a result. Synthesis is going the other way, providing a straight shot proof from the hypotheses to the conclusions. The whole combination, analysis and synthesis, was a standard fixture in a mathematician's education in the days of Archimedes. But the current environment supports only synthesis with formal training. It is a pity, and as I've said, it is a failing we are endeavoring to correct. Our presentation is very elementary, with examples taken from classroom experience. But mathematicians who take the time to learn the method of analysis and synthesis and to appreciate what it is able to do will find it to be more than just a technique. They will work with it, as have I, until it becomes a habit of thinking, and one to be used for doing mathematics even at the highest levels of the field. Mathematics is frequently simplified or oversimplified into being problem-solving or theorem-proving. But mathematics also has an exploratory aspect, discovering the mathematical results in the first place. Analysis has been shortchanged also in the way mathematicians write mathematics. From Euclid to the present day, books and journal articles overwhelmingly present only statements and proofs, which are syntheses, and almost never the derivation, which are the analyses. Nearly all theorems in mathematics are in an if-then construction. The substance of the if clauses are called the hypotheses. The substance of the then clauses are called the conclusions. Analysis and synthesis are two directions of inference. Synthesis is forward, going from the hypotheses to the conclusions with hence logic. Analysis is all backwards, as is its meaning as a Greek word, going from the conclusions to hypotheses with because logic. Thus, the dictum, never start with what you are trying to prove, is not universal. Starting with a conclusion is indeed inappropriate for synthesis, but it is the way to go for analysis. Some other kinds of doing don'ts may also be part of the liberation that analysis affords. But the method of analysis and synthesis ultimately is more than just working mathematics both forward and in reverse. Advanced techniques of analysis and synthesis can guide one to the result to be proved in the first place. In presenting this material, which ultimately is very rich, I have to start somewhere, and I have chosen to start simple. We shall present 4 topics: analysis and synthesis for solving story problems in a particularly correct and satisfying manner, analysis and synthesis for proving trigonometric identities, analysis and synthesis for deriving a result analytically that is later proved synthetically, and using the sheer liberation of analytic thinking to present mathematics in reverse of how it is presented synthetically. So, let's start with our first case, analysis and synthesis for solving story problems in an algebra class. Again, the method extends arbitrarily far upward. If you're underwhelmed by these examples, just think what they can do and will in higher mathematics. In a typical high school or college algebra class, students are taught some ad hoc advice for solution. The method of analysis and synthesis provides a firmer basis and will also carry heavy freight in the student's later work in science and technology. The method divides the solution into two parts with the names, you guessed it, analysis and synthesis. In the analysis, the first step is forming the analytic hypothesis. One assumes that a solution exists, assumes all the data given in the story, and assumes all the content given inside if clauses. Frequently, there is a fiat step, from the Latin fiat meaning let it be. For example, let x be the width of the rectangle. Again, my examples are very, very low level. The fiat step gets x on the scene in a deliberate and correct fashion. One then analyzes in the conventional sense of the term until one arrives at an equation. One then solves the equation and arrives at the now known value of x. Now everything on this slide extends. You can have several equations and several unknowns. Any math professor can say, yes, this is just the simplest case, of which more elaborate cases are in the same paradigm. But that was all analysis, and it was performed under the assumption of the analytic hypothesis. And so, after the analysis comes the synthesis. One redraws the picture with a now known value of x in the spot, or redraws everything. One verifies every particular of the story to be true about the synthetic picture. One reaches the synthetic conclusion that a solution does exist and is as advertised. The existence of a solution changes state from being something you assume to being something you conclude. And if the analysis does not check out, and if the synthesis does not all check out, but the analysis is all correct, then you have proved that no solution exists which satisfies the data of the problem. I have found that students take to story problems much better if they are given the full machinery for solving them. Everything should be as simple as possible, but not simpler, as the famous aphorism has it. A moment's reflection will show that the method just given is the only correct method for the solution of story problems. We in the profession may think we are doing students a favor when we simplify things by saying that not all of analysis and synthesis should be written out or even thought through. My own opinion is that mathematics is made harder, not easier, when we try to make things simpler than they really are. Let's move to our second case study about trigonometric identities. All too often, students are taught to verify trigonometric identities when real, honest-to-goodness proof is readily attainable. The simplest technique is to get from the left-hand side to the right-hand side by a string of equalities. One can also go from the right-hand side to the left-hand side. Another technique is to reduce both the left-hand side and the right-hand side to the same thing, and finish the proof by writing a bit of proper formality. As Euclid worded it, quantities equal to the same thing are equal to each other. That's all the formality you need to get this form of proof rigorized. But all those techniques allow working on only one side of the equation at a time. What should one do when, say, adding the same thing to both sides would be a wonderfully effective maneuver? You guessed it, analysis and synthesis, however difficult it is to pronounce. In the analysis, one again uses the analytic hypothesis. One assumes the trigonometric identity actually to be true for the purposes of analysis. One then plays with it and derives something obviously true. One then rewrites the analysis in reverse order so as to attain the synthesis. It is the synthesis that is the proof. Students then deposit their analyses into the analysis receptacle, which is the wastebasket in the front of the room. As a self-respecting mathematics professor, you still want to see the proof. Here is an example. Suppose we were to show for all real number theta, this thing over here will always match up with that thing over there. Since it's a little hard, we'll use the full technique of analysis and synthesis, which is the most elaborate of the methods of proving trigonometric identities, but also the most powerful. Some students avoid this because analysis and synthesis, because it's so much work, but others prefer it because it's so powerful, it's sure to get your trigonometric identity proved. But this one's so hard, probably you will need analysis and synthesis. So we start with what we're trying to prove. But this analysis is okay. We start with what we're trying to prove in analysis. Why don't we cross multiply? That makes sense. We'll multiply out on the left-hand side. Add sine squared to both sides. And surely everybody who's doing trigonometric identities at all knows that sine squared theta plus cosine squared theta is 1, no matter what theta may be. So we have our analysis, what we're trying to prove, and we end with what is obvious. Now, all too often, in my opinion, this stuff passes as a verification of a trigonometric identity in a high school or even college trigonometry class. It teaches every wrong thing about proof. But if we call it analysis, it's doing good. Now we have the synthesis with a few proof forms added. Let theta be an arbitrary real number for which everything that follows is defined. We properly declare our variable before using it. Surely 1 equals 1. The second presentation even confirmed that, if you think about it. Surely 1 equals 1. Thus 1 is the sine squared of theta plus the cosine squared of theta, as anyone would know who's doing trigonometric identities. Thus 1 minus sine squared of theta is cosine squared of theta. The reader can see, yes, we subtracted sine squared of theta from both sides. Factoring the left-hand side, we have this. Remember the good old difference of two squares? And we get this. Now divide both sides by cosine theta and also by 1 minus sine theta. This cancels off and ends up down there. One of the cosines cancels off and ends up down there. And we have this. But that's where we were trying to get to. Now, this is not quite the trigonometric identity because we don't have theta quantified. Therefore, since theta was arbitrary, for all real numbers x, for which everything that follows is defined, the quotient of 1 plus sine of theta with cosine of theta will be the quotient of cosine theta with 1 minus sine square of sine of theta. Quod erat demonstrandum. So now you see we are getting real proof, and it's very rigorous, very correct, the thing I think any professor of mathematics would like to see. I'll make some comments here. Notice that not only the order of exposition is reversed in analysis and synthesis, but all the reasons are inverted. Where we multiplied out in the analysis, we factor in the synthesis. Where we cleared fractions in the analysis, we introduced fractions in the synthesis. Notice that the inverse of a well-motivated step in the analysis is an ingenious, unmotivated step in the synthesis. Notice also that though the proof is the synthesis alone, if one really wants to understand what's going on, one may well want to see both the analysis and the synthesis. I will explain all of that with our leading example. If you see this, you just cross-multiply, just declare fractions. Even professors of mathematics don't like fractions a lot. Okay, we get rid of those fractions. We multiply out. And now, of course, we probably just get this to the other side and see that this is obvious. When we go into the reverse, though, surely 1 is 1. Out of the blue, we just say 1 is sine squared theta plus cosine squared theta, with no motivation whatsoever. Then with no motivation whatsoever, we subtract sine squared of theta from both sides. Then for no reason whatsoever, we just factor the left-hand side. It kind of feels good. Then for especially no reason whatsoever, we do this, and there it is. One totally unmotivated step, but perfectly valid, after another. Gets us from what is obvious to the result at hand. That's how these things look. Now, when I was a student in college, I had this technique down pat. I gave my professors proofs that were thoroughly, totally valid. And they had no choice but to give it full credit. But oh my word, what it was to grade one of my proofs where each and every one of my steps was totally unmotivated and didn't seem to make any sense at all, but gave you, of course, the result you want. Those of you who want to torment your professors will especially want to master this, to give your professors thoroughly valid proofs that are unusually difficult to grade. But this is just one of the many uses of analysis and synthesis. And the professor who wants to know, how did you do all this, you get that out of the analysis receptacle and show him. Let's move to our third case study, the theorem on vertex form. One can take the form a times the square of x minus h plus k, called vertex form, and show in class that it is the parabola, y being x squared, expanded and shifted, where a, h, and k are fixed real numbers, and where x and y are the denominations of the coordinate axes. Bring up memories. Could it be that the three parameters a, h, and k are related to the three parameters a, b, and c in this form, y being ax squared plus bx plus c? This form is called standard form. If there is a relationship, how are we going to find it? We can, of course, look up the result in a book, but suppose we wish to do better than that. How can we create the experience of actually deriving and proving mathematics in a high school or college algebra class? You guessed it! We employ the method of analysis and synthesis. Since the students have already done analysis and synthesis for every story problem in the course, they are perfectly familiar with it. It takes an entire day of class to do the analysis and a day to do the synthesis, but the results are very satisfying. The students have a real mathematical experience, and they sure put the end result to memory after seeing how much labor was expended to derive it and to prove it. Let me sketch all this. We're going to let a, b, and c be real numbers, and actually the a not being 0 will fall out of the analysis. I don't actually need that at this point. Consider them to be given. We seek, as required, real numbers a, h, and k, so that this standard form be equal to that vertex form as functions of x. Those math professors can follow what I'm about to say. Students will not be able to. One then expands the right-hand side, equates coefficients on like powers of x, solves the resulting 3 equations and 3 unknowns. It does not require Gaussian elimination. This professor can do all this as the students then sit in awe. We get this, that if all this is true, then big A here is this little a. And a is negative b over twice a, and k is c minus b squared over 4a. Observe the order of operations on that line. It is also true that k is ah squared plus bh plus c, plug h into your function, and also k is c minus ah squared, which is the swiftest way to find k. Okay, so you do all that. Starting from here, we get, if this is true, then that is true. But that was a huge analytic hypothesis, wasn't it? That a standard form could be equal to a vertex form. That must have been a bunch of analysis. Now we look at the synthesis. The theorem on vertex form, we quote it, let a, b, and c be real numbers with a not being 0. That follows from the analysis. Now, see these a's in the denominator? Better make sure they're not 0. We assert that this here standard form equals that there vertex form as functions of x, that should be a comma, where big A is little h is negative b over twice a, and k is found through this method, which works directly from the data a, b, and c. K is also equal to that, which is easier to memorize, and k is also equal to that, which is the swiftest. The proof is here omitted. You professors in the audience might want to write it out, even present it, but everything does follow readily. And notice, of course, we would never have thought of this unless we had done the analysis. The students do not mind seeing the proof, since they are habituated to seeing a synthesis after anything called analysis. The foregoing might look like a terror to inflict on any unsuspecting high school or college algebra class. So it may be, but it is not so terrible as the method of completing the square. By simply applying the theorem on vertex form, students compute their way to in a very straightforward manner. Let me start again. By simply applying the theorem on vertex form, students simply compute their way in a very straightforward fashion to the same result that the method of completing the square would give. And they feel like they are doing mathematics with real generality to it and real applicability. Unlike completing the square, where if the numbers get more complicated, you feel the method will break down. But obviously, the theorem on vertex form, no matter what numbers you plug in for little a, b, and c, you're going to find your a, h, and k. No doubt about it. Let us move now to the fourth case study, which I'm calling reverse inference. One can take the whole analysis and synthesis concept more broadly. How about doing some more forbidden things? Forbidden in synthesis, but allowed in analysis. Instead of switching ifs and thens, perhaps we could reverse the whole concept of deductive inference. Mathematicians, as noted earlier, emphasize synthesis to the derogation of analysis. We like to state theorems in the broadest manner possible, so that everything else follows as deductive inference, even as special cases of the big results. Even definitions are off-stated in huge levels of generality. But such broad generality in stating the result or definition at the outset causes it also to be stated in terms of huge abstraction. And only rarely has mathematical material been derived or discovered in such a way. Usually, the individual cases were done first, and the generalization came after. Can we, math professors, loosen up a bit and actually do it? Mathematicians generally chafe at any kind of inference from the particular to the general. Deductive inference is always from the general to the particular. But what if we loosen up? Going from the particular to the general is not deductive inference, but it must at least be something. Perhaps we could give it another name. In mirror image to synthetic deductive inference can be analytic superductive efference. Now, if you know enough Latin roots, that actually makes sense. Sound crazy? It surely is. But the now standard phrase deductive inference sounded just as crazy when it was first coined. Now, I must be clear about this. I am not saying that analysis is synthesis. I am not saying that superductive efference is the same as deductive inference. I am saying that analysis, as the term is being used here, has been an historical concomitant to synthesis all across the many centuries of mathematical development. Proving results in more generality than was ever done before is a standard part of mathematical practice. Synthesis alone constitutes proof, at least here on planet Earth, where because logic is not developed to nearly the same degree of sophistication as sense logic. But analysis is its mirror image, the mirror image to proof as we practice it here on Earth. I shall give this example again, a very low-level example of something that can generalize to arbitrarily broad heights. The concept of a function is oft stated with a huge generality and consequently a huge level of abstraction. What if we say that the important thing is for the student to know an input from an output? Surely the temperature outside is a function of the time of day. Below is shown a graph. The horizontal axis is of time. You can't see it. Here's 11 p.m., midnight, 2 a.m., 5 a.m. along this axis. The vertical axis is of temperature in degrees Fahrenheit. I can read this because I'm standing next to it. 50 degrees Fahrenheit, 60 degrees, 70 degrees, 80 degrees. Clearly, here in the United States, it does not do metric much in temperatures. Okay, so we can see temperature is a function of time of day. You don't need the graph to know that. You just stand outside and notice it gets warmer and cooler as the day progresses. Students readily read information from the graph, and I must acknowledge the National Weather Service for providing our graph today. It is only terminology to call time of day input and temperature output. The students readily answer any reasonable question put to them about time and temperature from the graph. Great! The students now have the basic idea. We can now strip meaning from both axes, and students will know input from output by placement. We have gone from the particular to the general with no problem. It is far easier for students to go from the particular to the general than the other way around. If students know how functions work in any one particular example, they generally will know what it means in any other. And if students don't understand the particular example, surely they will not understand the more general, abstract concept. And if they cannot understand the abstract, more general concept, they cannot understand the professor's method of presentation, this method of synthetic deductive inference from the general to the particular, because they do not understand the general concept to start with. Crazy as it sounds, it is the analytic, superductive efforts that is the effective mode of conveying mathematical understanding a lot of the time. I have here some general reflections. Of course, the method of analysis and synthesis has far more application than the underwhelmingly simple examples I have just given. The surest way out of a bout of mathematician's block is to have at least something to work from, even if it is the result to be proved, or a game of switching data and quasita, switching givens and requireds. Once one is past the mental block, one may make derivations. If one finds from the previously adopted if one finds a result from the previously adopted starting point, one may then examine the same amount of material afresh, starting from a proper set of hypotheses and reaching a proper set of conclusions. We all know what that process is called, however difficult it is sometimes to pronounce. Both students and professors of mathematics will find that analysis and synthesis is as powerful a tool today as ever it was in the time of Archimedes. Deriving mathematics is not some utterly formless task reserved only to geniuses, but instead derivation can be as structured as proof, and proof has definite and reliable structures available for it. Analysis is, after all, symmetrically related to synthesis. All professors of mathematics will be doing themselves and their students a service by finding space for the method of analysis and synthesis in our profession and our curriculum. The past may be prologue. and the ancient method of analysis and synthesis should be restored to its once honored place in the future of our discipline. And with that, my presentation is ended.